Most people think of infinity as something that goes off forever, without end. It seems simple enough. But the closer you look at infinity, the stranger it becomes. Have a look at these two sets. The counting numbers, 1, 2, 3, etc., and the squares of these numbers, 1, 4, 9, and so on. In some ways, they appear to be the same size. They're both infinite, and they can both be put in a list. But in another sense, the first set seems to be larger since it contains all the perfect squares, plus extra elements like 2 and 3. For a long time, mathematicians viewed infinity as simply the idea of continuing forever, avoiding issues of size. And then came George Cantor. Cantor developed set theory and spent most of his life trying to understand infinity. His results were both useful and bizarre. Cantor decided that two infinite sets should have the same size if you can find a way to uniquely pair off every element in the two sets so that no elements are left alone. So, for example, using the two sets from before, we could pair them up this way. 1 goes to 1, 2 goes to 4, 3 goes to 9, etc. Of course, mathematicians don't get away with proving things by drawing pictures and pointing. Because this was a simple example, we know we've paired up all the elements. But in general, you need an abstract rule to show that the pairing works for all numbers. To conclude that these two infinite sets have the same size, or have a one-to-one correspondence, Cantor suggested a simple mapping rule like n goes to n squared. Notice how this rule relates the two sets. Each natural number n gets paired with a unique member in the set of perfect squares, and all elements are taken care of. The mathematician calls this mapping a bijection. And notice how the geek demands that no squares be left out. But this is typical of geeks. So, all we've seen so far is that the counting numbers and the perfect squares have the same size. Taking the counting numbers as a starting point, Cantor calls this size of infinity Aleph naught, the idea being that there may be other Alephs out there. Aleph naught is known to be the smallest type of infinity, and all sets that have this size are said to be countably infinite, since we can match them up with the counting numbers, effectively putting them in a list. There are many sets that have this size of infinity. The counting numbers are clearly countable, since we can just pair up each element to itself, and we've seen that the perfect squares are countable too, since we can map each element to its square. It turns out that the set of even numbers also has size Aleph 0, since we can pair up each counting number to twice that number, leaving no even numbers out. Here's an interesting one, the set of all integers, positive, negative, and 0. The mapping may look complex, but the way it counts off integers is simple. It starts at 0 and works out, alternating between positive and negative integers. Notice that in doing this, the mapping will cover every possible integer. In a quest to find something uncountable, let's look at a set that's much more dense. The rational numbers. They include all the integers and all the ratios of the integers. Here's a few of them. The rationals are known to be very dense on the number line. There are infinitely many just between 0 and 1. In fact, there are infinitely many in small neighborhoods of each rational number, and it doesn't matter how small the neighborhood gets. That's pretty thick. Could you find a way to count them off? Cantor did, and I'll show you how it works with the positive rational numbers. This table contains all the positive rationals. The first row has all rationals with a 1 upstairs. The second contains all rationals with a 2 upstairs, and so on. An infinite list of infinite lists. How did he count them off in a single list? You can't go by rows, because you'll never finish the first row. Cantor's mapping counted them off by starting in the top left and sweeping through the table along the diagonals like this. Make sure you see that this will cover every positive rational number, all contained in one list. Notice how I skip over the 2 over 2 element, since it's actually a repeat of 1 over 1. Both of them represent the same number. Nonetheless, we have counted off all the positive rationals. And if you like pictures, Cantor has now paired every element in the set of counting numbers with every element in the set of positive rationals, nothing left out. It took only a few more steps to show that all the rational numbers, positive, negative, and 0, could be paired up with the counting numbers, which means the rationals, as dense as they are, have the same size of infinity as the counting numbers, Aleph naught. At this point, you may be wondering if every infinite set isn't countable. Cantor was wondering that too, so he went on to try and count off the members in a very thick set. Here's the continuum. It includes all the rationals like the integers and their ratios, as well as the irrationals, which involve numbers like pi, the square root of 7, and all other numbers with infinitely long and unpredictable patterns after the decimal. Can we count these off? Cantor says, no, you can't. So how does one go about proving that you can't write all the numbers of the continuum on one list? Cantor used proof by contradiction. He showed that for any infinite list that you give him, he could always look at it and find a number that's not on the list. In other words, you could never give him a complete list, because he could always look at it and find something that you missed. Here's how he did it. Consider this list of real numbers. I'll call the number I'm creating beta, and I'll make it between 0 and 1. Now the idea is to make it different from each number on the list one at a time. Take the first number on the list. Notice in its first decimal place is a 2. I'll put a 1 in beta's first decimal place, and this will guarantee that my beta is different than the first number on the list. The second number has 3 in the second decimal place, so for my beta, I'll put a 1 in the second decimal place. Beta is now different than both the first and second numbers on the list. The third number on the list has a 1 in the third decimal place, so I'll switch to 2 to guarantee that my beta is different from the third number as well. Continuing in this way, we have a rule for creating a number that's different than every number on the list, so no list can contain all real numbers. The result is that the real numbers are not countable, and thus represent a higher size of infinity. If you like pictures, we've shown that even though you can map each counting number to a unique real number, there will be real numbers left unpaired. Finally, we have a new type of infinity that seems to be larger than Aleph Naught. We call this infinite size C to represent the size of the continuum. Now take a look at these sets that have the same size as the continuum. Cantor showed that any interval of the continuum, no matter how small, has the same size as the continuum itself. One mapping that pairs up all the elements of these two sets does the following. Take the interval from A to B and wrap it up into a semicircle like this. Then, from the center, you draw a line down to the continuum. Notice how it pairs up one point on the curve with one point on the real line. As the mapping sweeps through the semicircle, every point on the curve gets paired uniquely with every point on the continuum. The result is that the interval from A to B has just as many elements as the whole real line, since we paired off all the elements with a one-to-one correspondence. So the interval AB and the continuum both have infinite size C. This next example is even more startling. Cantor showed that every point on a two-dimensional square can be paired up one-to-one with every point on a line. The result being that the two-dimensional square is made up of exactly as many elements as one of its edges, both having the same infinite size as the continuum.